last lecture only, we studied that the density of states per unit energy per unit volume in conduction band is given as 4 pi into 2 effective mass of electron raised to the power 3 by 2 divided by Q of Planck's constant into E minus AC. Also we know that the number of electrons per unit volume in the energy range dE is the product of the density of states and the probability of occupancy Fe. Thus, the total electron concentration is the integral over the entire conduction band, ranging from minima of the energy EC up to infinity. Now, we simply have to solve this expression. Now, we have to assume that Boltzmann approximation is valid, which is generally true as E minus EF is several times greater than KT under normal conditions. And you also know after Boltzmann approximation, we will get the expression for Fermi diapolaridity function to be equal to exponential of negative within bracket E minus EF divided by KT. And also here this term is representing the Fermi diapolaridity function. Now we have to replace this term by this term. Now see carefully. We are trying to change this expression so that we get the final expression in terms of E minus EC. For doing so, we have to rearrange this expression as E minus EC plus EC minus EF. Plus and minus EC will cancel each other. Divide by KT. Now, we will separate this expression as exponential E minus EC KT multiplied by exponential EC minus EF divided by KT. Now we will put this rearrangement in this particular equation, which will eventually give us Now we will bring out the constant term from the integral. I hope you have understood until now, and we have to use the next slide for proceeding further. Now we will change integral variable to z from E. The value of z is given by E minus EC upon KT. And this is the main reason why we converted the whole integral expression in terms of E minus EC. Differentiating will give dE upon KT. We have two expressions. One is del E is equal to KT into del Z. Also, E minus EC is equal to KT into Z. Now, we will put the value of E minus EC in the integral expression, which will give us the value of the integral points will be changed to 0 and infinity. You have to simply put the value of the upper and lower limits of the integration to this equation and find the value of corresponding z value. we will bring out the KT term out of the integral expression. This particular function is nothing but gamma function. I will not be going in much detail because you have to study it eventually in engineering mathematics. So for now, you just remember that the value of this expression is equal to under root pi divided by 2. We will study gamma function in engineering mathematics, so you need not to worry about it. So the final value of electron concentration in conduction band comes out the final expression of electron concentration comes out to be 2 into within bracket 2 pi effective mass of electron into kT raised to the power 3 by 2 divided by q of Planck's constant into exponential of negative within bracket EC minus EF divided by kT. But in the last lecture only, we studied that if Boltzmann approximation is valid, we had another expression of electron concentration in terms of effective density of states, which was electron concentration N naught is equal to effective density of states Nc multiplied by exponential within bracket EC minus EF divided by kT. Now, if you compare these two equations, then we will get the value of effective density of states to be equal to 2 into 2 pi effective mass of electron into kT raised to the power 3 by 2 divided by cube of Planck's constant. This is the formula which describes the relation of effective density of states with temperature. And this particular formula is very important. So you must learn it.